So this lesson is going to begin with a conversation back into something that we did earlier in terms of inverse function. So this lesson is only called the inverse sine function. But before we can get there, we're going to talk about what it means to be an inverse function in general, how do we get it, and that sort of thing. You do not need to copy these pictures down. They're really nice pictures, so they're just for us to look at. So in this first little box over here, okay, how would you describe this function? What function is this? This is the function. Yeah, x squared. This is the quadratic function, right? And what test can we apply visually that will tell us whether or not we're looking at a function? The vertical line test, right? We all agree that that function x squared passes the vertical line test, and we all agree there's those 3 points there have 0, 0, 1, 1, 2, 4, no problem. Okay, question for you though. Does it pass the horizontal line test? Oh, look at you guys, man. You must have had a great pre-calculus teacher. Wow. No? Okay. Or not. Okay, so yeah, it's not one-to-one, right? Which means that it doesn't have an inverse, right? The inverse does not exist. So the inverse function we cannot talk about. However, take a look at this middle drawing here, okay? This middle drawing here is the exact same drawing as before. This is f of x is equal to x squared, but I've changed something, right? I have restricted something. What have I restricted? I've restricted the domain for what values? Yeah, 0 to positive infinity, right? 0 to positive infinity. That's the restricted domain. Okay. So now that I've restricted the domain from 0 to infinity, right? Then does it pass the horizontal line test? It sure does. That means that it does have an inverse and it's one-to-one. So the third picture I have over there is still the same picture with all those points 0, 0, 1, 1, and 2, 4, but with the inverse on there, right? So this is the line y equals x, and I have clearly drawn for you how to get the inverse, which is that green graph right there. And the inverse for the green graph, of course, this is the function f of x equals the square root of x, right? And this, of course, is the function f of x equals x squared. So we can't start to talk about the inverse of a function that's not one-to-one until we restrict the domain, and then we can finally talk about the inverse of that function. Does that make sense to you so far, the story how it's developing? Okay, so we start with a quadratic. It's a function, but it's not one-to-one. We restrict the domain. Now all of a sudden it is a function and it's one-to-one. Now we can then talk about its inverse. That's the story, right? It's a very simple story, and we've seen that before. Well, guess what? For the sine function, it's the exact same story. And here we go. Check it out. I'm going to start with the function that we all know and love. And what is this function? This is the function f of x is equal to the sine of x. Okay, we've talked about this for a while now. We've studied it. I've given you I've given you a few critical points that we've been looking at so far in this unit, right? Namely 0, 0, pi over 2, 1, so on and so forth. And we all agree that this is a function because it passes the vertical line test, right? But however, it does not pass the horizontal line test because I could draw a horizontal line, for example, right there, and it doesn't pass, therefore it's not one-to-one, doesn't have an inverse. So what did we do? We restricted the domain, right? So that's what I'm going to do. I'm going to restrict the domain from negative pi over 2 to positive pi over 2. Okay, so I'm going to restrict the domain just inside this box right here. Okay, you see that? So look what I'm going to do. That box is now going to be drawn for you right down here. Okay? You guys still following along? So now all of a sudden, I have, this is still f of x is equal to the sine of x. It's still all good. But I have a restricted domain. And what is my new domain that I have restricted? Negative pi over 2 is going to be less than or equal to x, less than or equal to what? Positive pi over 2. Okay, now on my new restricted domain, does it pass both horizontal and vertical? Yes. It does. Therefore, it has an inverse. Okay? So the sine inverse function does exist, but it only exists on a restricted domain of the sine function, namely that domain right there. that I've just written down for you. So this is an important piece to remember, okay? And it's part of the story here. Okay, now if you look at this next picture, I have all these pictures here for you. If you look at this next picture over here, what am I trying to set up for you?
Secant line so you can draw the.
Yeah, that's not the secant line. This is still the line y equals x, right?
So you can draw the inverse.
Draw the inverse. Can you imagine what the inverse is going to look like, right?
Reflected across that.
It is reflected over that line, right? So how do I find 3 easy points on the inverse? Exchange the x for the y. Absolutely. So if I was going to sketch the inverse, I'll show you the real graph in a second. Well, 0, 0 would be there. Instead of pi over 2, 1, what would be there? 1 comma pi over 2. So it would be something like this. It would be reflected across, right? Instead of negative pi over 2, negative 1, what would be there? Negative 1, negative pi over 2. So something right about there. So I would have something that would be looking like this. Right? That's kind of a quick and dirty sketch of the inverse sine function, right? Well, here is what it really looks like, right down here. Okay? So there it is. I've now removed everything, and we end up with this down here, and this is the function f of x equals sine inverse of x. And that's where the story picks up. All right? So there's a lot of referencing back to what we did in terms of restricting our domains and understanding that we can't even have an inverse sine unless we restrict the domain on the regular sine curve. Okay? So we choose negative pi over 2 to pi over 2. We restrict the domain. We draw the graph. We then invert x for y, or switch x for y, because we're finding an inverse function. And we end up with this cool orange graph. And the way that we say this is sine inverse of x. Sine inverse of x. Now, what this means, you have to know what this means. So I'd write this part down. This means the angle whose sine is x. So we are going to be looking for angles whose sine is x. And we're only going to be looking for angles that live between negative pi over 2 and positive pi over 2. Okay, so what do we do with these inverse sine functions? Well, we use them to evaluate expressions like this. So we're going to start off with some known trig functions that are on the unit circle. So you might want to have your bite size out. It might be helpful to you at this moment in time. But we have to be able to read this and understand where it's coming from. So we'll do a little bit of analysis on this, all right? So when you see this statement, I really hope that you understand in English it means this. It means we're looking for the angle, and I'll call that angle theta, whose sine is what value, you guys? What's the value here? Is root 2 over 2. Okay, so that's what we're looking for. Yeah, that's what we're looking for, right? Now we have to keep in mind a few things. You'll always see me draw this picture, okay? Whenever we are dealing with the inverse sine of x, okay? It's on a restricted domain for the sine curve, right? And what was the restricted domain? It was between which two values of theta? Yeah, thank you, Ken. It is between negative pi over 2, which is down there, and pi over 2, which is up here, right? That's my restricted domain.
Should there be a negative 1 or just a negative sign?
Oh, thanks, yeah, inverse sine. I should put this somewhere else. I will. So let me rewrite this guy. So negative pi over 2 is down here. Pi over 2 is up there. Quadrant 1, and 0, of course, is here. And then quadrant 1, and then this is quadrant 4. Okay, so inverse sine only exists on the domain for the regular sine function between negative pi over 2 and pi over 2. So I'm only dealing with values in quadrant 1 and quadrant 4 only because of my restricted domain. You guys get that part? So the nice thing about this is this. Everything in quadrant 1 is positive. Sine values in quadrant 1 are positive. In quadrant number 4, sine values are negative. So this is really nice for us because now I know exactly which quadrant I'll be working with, either quadrant 1 or 4, depending on whatever this value says, right? And that value says positive root 2 over 2. So am I looking in quadrant 1 or am I looking in quadrant 4? I'm looking in quadrant 1, okay? So now I can draw this picture, okay? Yeah, all students take calculus, you got it, yeah. So here's what I want. I want the angle in quadrant 1 whose sine value is what? Root 2 over 2. So I'm looking for the y component of the angle whose sine is root 2 over 2. Exactly. It's 45 degrees, right? It's 45 degrees, but we give our answers in radians, so that would be pi over 4. So therefore, all this stuff just equals pi over 4. And that's all we're doing. Okay, here we go. We are taking a look at the expression inverse sine of root 3 over 2. And by the way, that doesn't mean 1 over the sine. That's not what that negative 1 means. This does not mean cosecant. Okay, just as a side note, some people get confused with that. Right. So here we go. I'm dealing with an inverse sine function, so I'm either going to be in quadrant number 4, or I'm going to be in quadrant number 1. This is negative pi over 2. This is positive pi over 2. I can only pick 8 radian values that are in between those. Everything in quadrant 1 is positive. Everything in quadrant 4 is negative. Which quadrant should I be in? I should be in quadrant 1, right? So here we go. So I'm going to draw a picture in quadrant 1, and I'm looking for the angle whose sine is root 3 over 2. That angle must be pi over 3. So this whole thing must be pi over 3. Okay, let's do the inverse sine of negative 1/2. Well, I have an inverse sine function. This is negative pi over 2. This is positive pi over 2. My angles are somewhere in there. Here's quadrant 1. Here's quadrant number 4. I have a negative value. So am I in quadrant 1 or 4? I'm in quadrant 4, right? Because this is positive, this is negative down here. So I'm going to draw a picture that highlights quadrant number 4. Okay, and I'm looking for the angle whose sine is negative 1/2. So where on the unit circle does this give me negative 1/2? Everybody says 11 pi over 6. That's not the right answer. The reason that's not the right answer is because that angle is here, isn't it? That's outside of my domain.
It's negative pi over 6.
So instead, we say this. It's negative pi over 6 is the correct answer. Ah, very tricky, very tricky. Okay, you tries. You tries these, okay? Let's do A and B right here. All right, let's get going here. Anybody got an answer for part A? Anybody got an answer for part A? Pi over 3, I agree. Wait. It's negative pi over 3. Negative pi over 3. That's what I got for that one, okay? Shh. I got a pi over 6 for part B. Do we agree with that? Yes. Awesome. Great. Okay, here we go. Let's make it a little bit more interesting here, right? So, what we're doing is we are extending our angle measure to not just those nice easy ones like 30, 45, 60, right? We can apply this to any general angle measure that we want, provided that we stay within the domain for regular sine function. Okay, if you walked into the classroom and just saw this, it'd look very kind of intimidating, right?
Yeah, it would.
So you now have to fall back on what this means. This means the what? The angle whose the angle theta whose sine is what? Is negative 3/5 is this, okay? So you have to revert back to that. When you understand what that means, you just take the tangent of that angle. That's what that means, all right? So for inverse sine, think about it, right? Where am I going to be? I can only be in quadrant 1, or I can only be in quadrant number 4. Which one am I going to be in? I'm going to be in quadrant 4 because I have the angle whose sine is negative, right? So here's what we do. We draw the angle in quadrant 4.
Are you just drawing the angle?
Yeah, just some sketch of an angle. Yeah, the answer is all in the sketch, okay? Now, what do I know about that particular angle? I know that its sine is negative 3/5. So you'll recall that when we extend these angles to general, outside the unit circle, right? In anything, the sine is defined as y over r. Remember that?
Negative.
So this is negative 3, and the r is 5. See that? It's defined as y over r for sine. Well, that makes it very simple, because the missing side is just going to be a 4, and it would be positive because this point I could get to that point by going 4, negative 3, right? So now what do I want? I want the tangent of that picture. Now it makes sense. So the tangent of the picture is what? Is negative 3/4. So the tangent of the inverse sine of negative 3/5 is a negative 3/4. Alright, we want the cosine of the inverse sine of 4/5. The answer is always in the drawing. So I'm going to go straight to my drawing. I know I have to be in quadrant 1. So I want the angle theta whose sine is 4/5. 4 must be here since it represents the opposite. 5 must be here since it represents the r, the y value, and then the r value. And then lastly, I would have the 3, because there's a 3, 4, 5 triangle. And what do I want? I want the cosine of the picture, right? So the cosine of the picture would be what? Yeah, you're right. The cosine would be 3 over 5, wouldn't it? I had it right. Yeah, the cosine would be 3/5. Okay. Here we go. We want the cosecant of the inverse sine of negative root 2 over 2. Okay, the answer is still in the drawing. I know I'm in quadrant 4. Okay. I have some angle theta, right? And what I know about that, I know that the angle is the sine is negative root 2 over 2, right? So that means that the x value has to be what? No.
Negative.
No. Rad 2, right? This is a 45, 45, 90, right? The sine whose angle is negative root 2 over 2, I could write it just like this. This is the picture I could draw. So what do I want from this then? I want the cosecant of that angle. And the cosecant is defined as r over y. So that's going to be what? The value of r is what? 2 over y, which is a value of negative root 2. Can't leave it like that. Multiply top and bottom by a root 2 over root 2. That gives us negative 2 root 2 over 2, negative root 2. So therefore, the answer that we're looking for is negative root 2.